So hello everyone, I will present you my work on a framework in order to simulate tissue morphogenesis. We call it PalaCell2D. So a few words about morphogenesis. In biology, it's interesting to think about the mechanism that govern how the tissue and the organism are growing during the embryogenesis. And it can be a mix between some mechanical process and some biological process. We want to simulate this in silico in order to be able to better understand the biological and the mechanical process that are underlying the morphogenesis. And it's also interesting to be able to test and quantify the impact of the parameter on the model to be able to test, because it's easier to test it on simulation that with a biological experiment that take a lot of time. So in my model, I use a fully resolved model. As I called it, I will explain a little bit after. We use a polygonal description for the cells. The cells proliferation are driven by pressure. The cells boundary are moving following a Newtonian dynamics, and we have some coupling with LBM for the signaling. And we are interested in tissue growth driven by signaling, cell proliferation under constraints, tissue deformation, cells polarity, and stuff like this. So for the cell description in my model, you may know the Vertex model in order to simulate a cell. So in a Vertex model, you have only a few points in order to describe the cell boundary. And between 2 points, it's a cell edge. And the edge is in common between two cells. In my model, as I told before, it's a fully resolved model, so the vertices, there are a lot more vertices on the cell boundary, and each cell has its own cells boundary, which allow us to have better shape, more realistic shape than just straight line. So each cell is defined as a polygon with a lot of edge, and as we want to add the dynamics on that, we work mostly on the vertices. So we can also see the cells as just a particle structure, which is easy to connect after the edge if we want to do some graphs. As we want that the cells can grow, we have to choose a mechanism in order to allow the growth of the cell. So we want, in this model, we choose to have a constant vertex density on the cell surface. So when two vertices are too close, we have to remove one of them. I have to do with this red point there. And when two vertices are too far, I have to add a new vertices, like this blue one there. For the dynamics of the cells, we have different level in order to model modeling the dynamics. We have the vertices level, where we have the Newtonian dynamics. We have also cells interaction. When we have more than one cell, the vertices have to interact between them. We have also the cells dynamics level, which is where we can have a growing process, and we have also ability to add external mechanism like external forces or coupling with a signaling. So for the cells dynamics, as I told you before, we use the pressure in order to be able to modelize the growth of the cells. So we link the pressure to the density. So we want that when the density is too high, the cells are growing. When the density is the target density, the cells stay the same. And when the cells has under density, the cells have to shrink. To implement that process, we, as I told you, we link the density to the pressure inside the cells. So it's not an absolute pressure, but just a different, a relative pressure. And to be able to have a cell proliferation, we have to add a mechanism that increase the mass of the cells, that change the mass of the cells. So it is one example of a function in order to have cell proliferation. And as we have, we can have multiple states for the cells. When the cells are not proliferating, the cells are relaxing. So we can have something like that in order to go to the target density. So if the area of the cells is too high, the mass will reduce, and if the area is too low, the mass will be added. In terms of vertex dynamics, I represent just a little three vertices in order to see the different forces. We have forces acting on vertices. So it's a normal of the vertex at this point. The first force that we have, as I presented you before, is the pressure force, which is parallel to the normal at this point. We have also a bending force, which is in the opposite direction of the normal, and this force try to have a flattening between the point. You want to the force try to align the normal of the different vector. And we have also a spring force in order to adjust the position of the vertices among the other. So this force is not related to the normal direction. So in the case of just one cells, we have these three forces that give total forces that is used in order to move the vertices. When we have more than one cells, we add interaction between cells. So for that, we have to decide of a range of interaction. In this case, it's represented by this dotted line. And we have two different forces that are related to the interaction between the cells. The first one is the adherent forces, which is attractive repulsive forces that try to keep the cells at a given distances. So if the two vertices are too close, the force will be repulsive, and when we are in the range of interaction but far enough, the force is attractive in order to set the distances between the two cells at d0. The other interaction forces is the contact pressure force. As we use pressure, we have to transmit the pressure from one cell to the other. So in this case, we just have the total pressure coming from the connected vertices from the other cells with a weight that, because this point has two neighbors, so you have to be divided by 2 in order to don't sum up too much pressure forces. For the external pressure or signaling or stuff like that, I will present just the signaling part because we use LBM. So we simulate chemical signaling to switch the cell states between growing and relaxing. So in order to have more different behavior that just cells in growing every time. In order to simulate that, we use an advection reaction diffusion model on LBM on the D2Q5 lattice. We have a reaction term. In this case, we have only one cell that is the source, and the chemical is decreasing on all the space outside these cells. So in order to coupling the Newtonian part and the LBM part, we have to know where the cell is and choose if for each LBM point of cells in the grid are inside the cell or outside the cell. And after that, we just have to sum up all the signal on those cells in order to have the total signal for one cell, which give the ability to switch between the two cells. So now I will show you some test case that we have. So the first one is the tissue growth. So first, using a signaling, so is as I present before, we have one cells that are producing some chemical signal that allow the neighboring cells to be in growing in proliferation mode. So in black, it's the cells in proliferation. And in white, the cells are in relaxing mode. And we did the same, but without signaling. We end up something which is a lot quicker, but it causes some problem because the cells are growing everywhere at the same rate, so it's give less realistic picture that with the signaling. In order to validate this simulation, yeah, perfect. We compare with one experiment made by Fradifar that shows that number of neighboring
5 minutes.
cells is close to 6. It depends on the cells. It's different for every kind of cells. With more cells with 5 neighbors than 7. So this is the result that I obtained with my simulation. So we can see that we are very close to 6 with the mean number of neighbor, and we have more 5 neighbor than 7, which seems correct according to the experiment. The other test case that I will present you is growth under circular constraint. So in this case, we don't have chemical signaling. But we have the two states of the cells. The cells proliferation are controlled by the pressure, and we have an external deformable capsule that the cells can push at some point in order to grow, but exerts a force on the cells. So we expect that at some point of the simulation, the proliferation will stop, and at the end, the remaining cells that try to divide, so that are proliferating, are in the at the interface between the tissue and the capsules. And also the fraction of proliferating cells stay constant at the beginning and at some point start to decrease. So this is the simulation that I did. So as previously, the black are proliferating and the white are in resting mode. So you see that at the end, we have black only and the boundary. And there, you have the fraction of cells that are proliferating for the time. And we have a constant number at the beginning, and after we have a decreasing part, which is what we expect. I will just present you 2 ongoing work. So we try also to simulate cell proliferation inside a strip in order to see how the cells confined start to invade a strip. So at some point I will remove a wall there and the cell will invade this part. And another work doing by a bachelor student in your group was to add cell motility on my framework in order to try to replicate some experiment. So in conclusion, PalaCell2D, the result that I have for tissue growth are compatible with biological experiment regarding the number of neighbors. The coupling with external constraint like signaling or force or wall allow to simulate easily a lot of different biological experiments, and the high resolution of the cell surface allow to add some motility model like in the bachelor project. So thank you for your attention.
Okay, thank you, Conradin, for your interesting talk. If there is someone that can ask something, can write in the chat to book. Okay, you can ask Tim.
Thank you Thank you very much. I like this presentation. It's fantastic what you can do with this model. It's great. I have two questions, but maybe one is enough for now. Regarding the advection diffusion model that you use for signaling, do you also have a model that takes into account the resistance for chemicals to enter the cells, to go through the membrane?
No, we don't add boundary immerse boundary method or something like that in order to prevent the chemical to go inside the cells.
Okay, okay. It would be interesting for the future to see how the presence of a cell is affecting the diffusion of the chemicals. Just a quick follow-up, if I may, because you mentioned experimental data. Have you compared your simulation results with experiments?
We are trying. It's an ongoing process.
Okay, thank you very much. A very nice presentation. Thank you.
Thank you.
Okay, thank you again. Okay, we can go to the next talk with Fabio Guglietta, mesoscale simulation of transient red blood cell dynamics. Okay, you can start. Thanks.
Okay, thank you. Can you see my screen now? Okay, so can you see and hear me?
Yeah?
Okay.
You hear well. You can start.
Okay, thank you. So good morning to everybody. Today I'm going to talk to you about our work that is about mesoscale simulations of transient red blood cell dynamics in collaboration with Mark Behr, Luca Biferale, Giacomo Falcucci, and Mauro Sbragaglia. And I am Fabio Guglietta, a PhD student at the University of Rome Tor Vergata, the Aachen University, and the Cyprus Institute. So why do we study red blood cells? In our work, the reason lies in some particular medical devices. They are called ventricular assistant devices, VAD. And they are just mechanical pumps, and they are used to assist in blood circulations in patients with heart failure. Since in these devices the shear is very, very high, in particular in the impeller, there is the risk of hemolysis. In general, hemolysis happens when there is a release of the cytoplasm, that is the fluid inside the membrane. And it could be very, very dangerous for the human being. And on the right side here, you can see a realistic red blood cell, while here we have a representation of our 3D mesh that we use to simulate the red blood cell membrane. And red blood cells are particular cells because, for example, they are enucleate, so they don't have a nucleus. In particular, in fact, inside the membrane, there is just a fluid, whose viscosity is about 5 times higher than the viscosity of the surrounding fluid, the plasma. And so here you can see a picture of VAD. This is the impeller, and in this sketch you can see just one red blood cell, and this is just to show what happens to one red blood cell. But if you see at the characteristic length of these devices, you can imagine that there are billions of red blood cells. So the red blood cell goes inside the impeller, then it is shaken, stretched here, and it goes out. Now, the question is, how does it feel? I would say not very well, but we are physicists, so we are interested in quantify this. And to do so, we can adopt the Aurora's model. And this is a model where the red blood cell is assumed to be like a droplet. So here you can see an ellipsoid. And the deformation is described by this morphological tensor S. And this is an evolution equation for S. And in particular, here you can recognize 3 main terms. Each of these is characterized by one of these parameters, so F1, F2, and F3. And they are connected to different behavior of the red blood cell membrane. For example, F1 is connected to the relaxation process, F2 to the deformation, and F3 to the tongue threading motion of the membrane. In particular, in this work, we will focus on F1 that is the inverse of the relaxation time of the membrane. So we perform 3D simulation in the framework of the immersive boundary lattice-Boltzmann method. Of course, I don't want to go into the details of the lattice-Boltzmann method. This is just to say that we are adopting the D3Q19 scheme. And in particular, we use the immersive boundary to couple the membrane with the fluid. So this is the membrane model. In this model, the elastic energy described by these two terms. The first one is the strain term, and for the strain, we adopted the Scalac model, that is a constitutive equation, which depends on these two elastic moduli that are Ks and K alpha. One is related to the shear, and the other one to the area dilation. And then it depends on the strain variance of the single element of the 3D triangular mesh. While for the bending term, we adopted the Helfrich formulation. And here, this is an angle, theta ij, that is the angle between two elements. So those are the normals of the elements. And this is the angle between these two normals. And the idea of the bending term is to ensure the recovery of the shape at rest. So once we have the free energy of the membrane, we can compute the force or not, just computing the derivative of the free energy with respect to the position of the single nodes. But this is not the end of the story, because if we want to look at the times of the dynamics, we have also to include the viscosity of the membrane. To do so, here I reported a sketch taken in some sense from the electronic world. And here you can see a dashpot, which represents the viscosity part, and two springs, key first and key. And they represent the elastic part. So now we can see that we can connect these two elements in different ways. For example, if we connect in series the dashpot and the spring, we have the so-called Maxwell model. This model can describe the relaxation process, but it cannot describe the creep experiment. But if we connect the dashpot and the spring in parallel, we have the Kelvin-Voigt model, which can describe, on the contrary, the creep, but not the relaxation. So the next step is trying to, for example, put the dashpot and the spring in series and put them in parallel. And the result could be that it cannot describe neither the creep nor the relaxation, but luckily it's not the case. And it can describe both creep and relaxation. So this is the model that we need, the standard linear solid model. So in our code, we compute the viscous stress. And from the viscous stress, we can compute again the force on the node. And in particular, in our simulation, we use the shear membrane viscosity and the dilation membrane viscosity with the same values. So this is our friend, so the red cell, the 3D triangular mesh. Here you can see some characteristic dimensions and also the moduli that we used. But I want to focus on these two figures on the bottom. On the left, you can see the stretching experiment. On the right, the shear experiment. So what we did is trying to force the membrane in two different ways, and just to see if there is a dependency on the kind of mechanical load. So on the left, as I said, there is the stretching experiment, where here you can see the two silica beads that are used to stretch the red blood cell. They attach it at the end of the red blood cell. And this is to simulate the experiment in optical tweezer. So we stretch the red blood cell through these silica beads. While here on the right, you have the shear experiment, where the red blood cell is deformed with shear flow. So here you can see that it deforms according to the shear flow. So this is a short movie about the stretching experiment. As you can see here, we select two areas where the force is applied. So we apply the force, we measure the axial and transversal diameters, and we compute the elongational index, both during the loading and the relaxation process. And then we follow this elongational index in time. Here on the left, you can see the steady state value. So when the RBC is fully stretched, and we compared our result with the one from Suresh that is an experimental result, and we found a good agreement. What's interesting here is that we tried also to vary the membrane viscosity, and as expected, there are no differences in the steady state shape. While there are differences when we look at the time evolution of the main diameters. So as you can see here, during the loading, the final result is the same, but the time that it takes to reach it changes according to the membrane viscosity. And about the relaxation time here, I reported two plots. On the left, we can see the elongational index at varying membrane viscosities. So as you can see, increasing the membrane viscosity results in a decrease, in increase of the relaxation time. Here I reported also an experimental results from Mills et al. While if we fix the membrane viscosity and we change the load strength, we can see that increasing the force will decrease the relaxation time. Both data are fit with this exponential function. So here I reported all the results of the relaxation time in milliseconds at varying forces and membrane viscosities. So what is very interesting is plotted here in the inset. So here we plotted the relaxation time and normalized by the relaxation time for the smallest forces that we simulated. And here you can see that there is a collapse of results at varying membrane viscosities. This collapse shows that the functional dependency on the force can be factorized with respect to the dependency on the membrane viscosity. And I think that this result is very interesting here. It wasn't expected. Now, the experiment of the linear shear flow. Here again, we have the red blood cell at rest, and we select the shear plane, xz, and when the shear flow starts. As you can see, it deforms, not also that it rotates around the shape at rest, and then it relaxes to equilibrium. Again, here we computed the elongational index, and here we reported the main diameters when it reaches the maximum stretch. And as you can see here, on the contrary as before, now these diameters depend on the membrane viscosity. In particular, increasing the membrane viscosity results in a decrease of the deformation. Actually, it seems that there is no deformation for this value of membrane viscosity. So this is different with respect to the stretching case. On the left, again, we plotted the elongational index at varying membrane viscosity with the shear rate fixed. And again, we have the same results both on the left and the right that we had for the stretching experiment. So increasing the membrane viscosity will result in increase of the relaxation time. And here again, increasing the shear rate will decrease the relaxation time. Here we reported all the results that we had. So qualitatively is the same that we got before for the stretching experiment. The only difference now is here. Again, we plotted the relaxation time normalized by the relaxation time for the smallest shear rate that we simulated. And now there is no more the collapse that we saw before. Maybe the reason of this could be, for example, that now the red blood cell, when it's forced by the shear rate, it not only deforms, but it also rotates. So the energy injected is used in two processes, so the deformation and the rotation of the cell. And in the rotation is involved also the membrane viscosity, so this could be the reason that there is no collapse here. Now we want to compare these two results for the stretching and the shear simulation. And to do so, we have to report the relaxation time with the same load strength. So in one case, we have Newton. In another case, we have seconds to the -1. So what we did is just to compute the stress on the particle and report so the relaxation time versus the stress on the particle. So what we can see, they are not very, very different, but what emerges here is that increasing the membrane viscosity brings a dependency on the kind of the mechanical loads. But it is interesting also to note that for small forcings, for small load strengths, we have almost the same results, both from stretching and shear simulations. This is because when we use a small load strength, we are looking at the intrinsic property of the membrane. So it's not very, very surprising, this. And this result, so this relaxation time with this value of membrane viscosity is in good agreement with this experimental work by Chen et al., where they found this relaxation time about 150 milliseconds. That is almost the same that we got for the same, almost the same membrane viscosity. And also here, when we, in the case of zero membrane viscosity, we got something like of the order of the magnitude of 1 milliseconds. That is the same predicted by Evans in this work. And the reason of this time is in this formula where the relaxation time is written in terms of membrane viscosity here, but also in dissipation in adjacent aqueous phases. So there is another viscosity that is smaller than this, but not zero. So when this is zero, we can compute this and we get the result of 1 milliseconds about. So there is a good agreement in this case. Finally, we report here the relaxation time at varying membrane viscosity for small lead strength. So we select both for the stretching and the shear, the smallest load strength that we simulated. And here we can see that there is a linear dependency. We also compared our result with the same as Prado et al., and there is a good agreement also with them. So to conclude, in the limit case of vanishing load strength, the relaxation time is a linear function of the membrane viscosity. And more important, it does not sensibly depend on the load mechanism. While for finite load strength magnitudes, the relaxation time proves to depend non-trivially on the load strength. And what's next? There are two main paths, main ways. In the first one, we want to study the time response of red blood cells to a generic time-dependent strength rate, for example, to a sinusoidal signal. This is because it reproduces the main feature of the fluid, for example, in VAD. And the other way is trying to characterize the loading time, because now in this work, we focused on the second part, the relaxation part. So we have the RBC at rest, it deforms, then it reaches the steady state, and then it relaxes to the rest shape. This is both for the stretching and the shear. Now we want to look at the time during the loading part to see if there is something similar to the relaxation, if there is a symmetry or not. And so we are going to investigate also this. And okay, that's all. Thank you.
Okay, thank you, Fabio, for the really interesting presentation. If you have any question, please feel free to ask.
Can I ask a question, please?
Yeah, sure.
Fabio, great talk. I liked it. Very clear.
Thank you.
Do you have any idea what the effect of the membrane viscosity is on the shear viscosity of blood as a suspension, if you look at more than one cell? Have you looked at that?
Okay, no, we didn't look at more than one cell. Now we focalize just on one cell to get the intrinsic properties of the membrane, so just one cell. But of course, it will be interesting to study also more than one to see how it changes and how does it impact. Yeah, but we didn't do this.
Okay, thank you.
Yeah, thank you.
Other questions? Okay, if not, let's thank again Fabio. I think we may stop right now the first part of the session, and we will back in 10 minutes. we are a little bit late with respect to the initial schedule, so we have to shrink a little bit the coffee break, and we have only 10 minutes break. Okay, I hope to see you back in 10 minutes. Of stenosis growth on blood flow at the bifurcation of the carotid artery. So if James is ready, please, stage is yours.
Okay, thank you. Just to start with the usual question, can you see my screen and hear me all right?
Yeah, perfectly.
Okay, that's great. Okay, good morning, everyone. What I'm going to talk about today is the effect of stenosis growth on blood flow at the bifurcation of the carotid artery, which is the main artery in your neck, taking blood up towards your brain. Sorry, I'll just try and put this on full screen. There we go. So I'll start by describing the background to why we're interested in this, also the details of the numerical model that we're using before moving on to look at the results. Two sorts of results. One is looking at how the stenosis develops inside the artery, and the second one looking at the near wall hemodynamics. They're important because they are what influence, or one of the factors that influence the development of the stenosis. So we'll look at that before moving on to the conclusions. So I'd like to start with a little background about atherosclerosis. It's a very major cardiovascular disease whereby you get the deposit of plaque on the side walls of the artery. Now, before I started looking at this in detail, I was obviously aware that the big problem that can occur is occlusion of the artery. So if the plaque grows to such an extent that the artery is closed off, then that reduces or even stops the blood flow, in this case up to the brain, and that obviously has very serious implications. But actually, you can have equally serious consequences long before you reach occlusion. If you have a small amount of plaque on the wall of the artery, that can rupture, can break off, and then it can move through the bloodstream and block somewhere further upstream where the artery is narrower. As well as that, when there is rupture, you also get blood clotting occurring on the wall of the artery. That itself can grow and block the artery, or it can also break off and move upstream. So even if you have a small stenosis that is nothing like blocking off the artery, it can be very dangerous if you have a rupture occurring. Now, the development of atherosclerosis depends on many factors. There's a lot of well-known risk factors, things like smoking, high-fat diet, lack of exercise, obesity. But it also depends on the hemodynamic factors, the wall velocity, the wall shear stress, and also on the geometry and the shape of the artery. I've highlighted them in bold, not because they're necessarily the most important factors, but they're the factors that we're able to look at in the presentation today. How do we do the simulations? We run the simulations using a 2D artery model. Now, clearly, arteries are three-dimensional and you get three-dimensional effects. But due to the fact that we're running this over a large number of periods, and also where we have looked at results in 2 and 3D, the 3D results obviously give more detail of some fine structure of the flow, but the 2D simulations in the past have been shown to give a really reasonable representation of what's going on. So here's the artery we used. It starts with the common carotid artery at the bottom, and then it splits into two, the external and the internal carotid artery. In terms of the blood flow modelling, a fairly standard D2Q9 lattice-Boltzmann model. I don't think I need to go into the details of this here, but that's what was used. In terms of the boundary conditions, at the inlet, we used this velocity pulse here. That was derived from Holdsworth's physiological measurement
and it gives an indication of the velocity that's coming in at the bottom of the artery. At the outlet, we used an absorbing boundary condition just to absorb any pulse and stop any reflections coming back and affecting the results in our region of interest. In terms of the artery walls, we used this model by Go. I'll not go into the full details of it, but it removes the sort of step-like boundary function that you get if you just simply use the underlying lattice. The basics of what's happening with this model is if we have a boundary which is represented by the black line, and we have fluid, in this case blood, in the top right, and the solid wall to the left of that, then if we look at a point such as this point here, XF, if we want to calculate our new distribution functions here, it relies on all of our neighbours, and in particular, it relies on what would normally coming in from this wall site, but obviously that isn't there because that isn't within the fluid. And so what the boundary condition does, the algorithm calculates a fictitious distribution function coming in from this wall node up towards this site XF. And it does it by looking at what the density would be here and also what the velocity would be at the wall site. And it extrapolates the velocity based on the zero boundary condition actually at the boundary and the known value of the velocity at this site, XF. To do that, you need to have the value of delta. Capital delta here is just the normalized distance from the boundary up to the site XF. So it's ranging from 0 to 1, even if we're on a diagonal. And Guo suggested that this wouldn't work very well if delta was particularly small, and in fact suggested only using it for delta greater than 0.75. If delta was less than that, then we also look at this point here, XFF, which is another lattice step away. Without going into the details, these predicted velocity and density here are then used to find the equilibrium and also a non-equilibrium term to give you the distribution function that's coming in here. So that was the basic boundary. It's a fixed boundary. When we want to look at the development of stenosis, we obviously require that boundary to move. And the methodology that was used for that is explained on this next slide. I'll initially explain the original model as it was proposed, and then a slight variation to that, which we used in the work here. You can see the same sites. Here in the middle, we have the known velocity UF. Out here, the velocity UFF. We find a further velocity, which is referred to as U1, and that's the velocity exactly one lattice unit from where the actual wall is. And that is actually something that's very useful when we want to look at sort of things like near wall velocity. So that's a very useful term to have. Also, you'll see I've used a little delta to describe the distance between the boundary and the site UF. The reason for that is this isn't normalized, and so it's obviously 1 when we're going horizontally or vertically, root 2 if we're on a diagonal. And the idea with the model is that we run for a period of the pulse, a period of the heartbeat, and we look at the wall shear stress, and we time average that wall shear stress, and we find the point where that average time average wall shear stress is a minimum. And that's the position where the boundary is adjusted, moved into the fluid in order to represent the development of the stenosis. Here we did something slightly different. Rather than working with the velocity U1, which is obviously proportional to the wall shear stress, we instead used the expression at the bottom here for the shear stress tensor, which I think originally was in Artoli's thesis. The other thing I should say that as we move the boundary in. So if this site here was defined to be the point where we had the minimum wall shear stress, then we would move the boundary towards that site. And if the boundary was already quite close, we'd actually move it beyond the site, and that site would be removed from the fluid. Now, there's a lot of work being done on fluid structure interactions, whereby you have something moving, maybe pulsing through a period, and it's very important to look at the interaction of that motion on the fluid that it's moving into. So you'll get changes in pressure, changes in velocity. Here we expect to see a change because as the artery wall changes, then it's going to affect the simulation in the next period. But we're not looking for an instantaneous change. So when we make the change in the boundary, we don't change the velocity of the pressure at the neighbouring points. And indeed, if the boundary moves through the neighbouring point, we just remove it from the simulation. So we're not, strictly speaking, conserving masses or momentum. The reason that's okay is we're looking at very small changes, and then we're looking at a whole period to see how the flow over that period is changed by the change in the boundary. So what does that look like? Well, here we have our stenosis, our artery, the original artery being shown in black. And then we see as the model runs, the artery walls move, and TS represents the number of sites, grid sites that have been covered. So as the boundary moves through a grid site, TS increases by a value of 1. And this gives us an indication of the progression of the stenosis, but it doesn't give us an indication of the rate of progression. So it's giving us an indication of how that progresses, but no indication of where sometimes it might be happening more quickly, other times it might be happening more slowly. Obviously, it's not incrementing every single period as we're doing in this model here, but what we're suggesting is that after there is an incremental change, then it will stay the same for very many periods, but ultimately it will eventually change, and it's that next period, which is the next one that we're simulating. What the results show is that the plaque is laid down in layers. For the first 20 TS, it's sort of randomly done between the internal and the external. After that, it lays down a big layer on the external carotid artery on the left-hand side. Then it puts down a layer on the right-hand side on the internal carotid artery, and then it switches from one side to the other, laying down consecutive layers of plaque. With the external, the first layer of plaque is by far the largest. After that, there's just thin layers that are added on top. On the other side, we see with these different layers, we're extending further and further downstream through the artery. So that's what the plaque looks like. Before I look at the near wall hemodynamics, I just want to show this simulation of what the velocity looks like as it goes through. We get this original pulse, and then if I stop it here, as the pulse goes through, we get these regions on both external walls where we're seeing some vorticity generated. And I just want to show that just now, because I'll come back and discuss it in a bit more detail later. So what do the results look like? This is looking on the external carotid artery, and here we see just the displacement on the y-axis, and on the x-axis we have the time going through a period. And what we're plotting is that value of the velocity u1, so that's the velocity 1 lattice unit from the wall, and we're looking at the tangential component. That was calculated by looking at 10 wall points either side to get the direction of the wall. Looking along the x-axis, we see the initial fairly low velocity. We then see the peak, then that drops off, and there's a secondary peak. So the velocity profile looks very much like the pulse that we put in at the bottom. But in this region between 40 and 45 millimeters, we see that the peak is much smaller, and we also have this large low velocity region which actually persists for some time and also moves some distance upstream. That was for the original healthy artery. Once that first layer of plaque had been put on, the image on the right shows something that's fairly regular across all positions. So we've removed this region where we see these vortices forming, where we see that low velocity. If we look at later times, we don't see a great deal of difference, but we do see this region here becoming more uniform. So we don't see this strip going through later in the period. But other than that, we don't see a great deal of change. The internal carotid artery on the other wall, not say too much because we see a very similar picture in that we see a break in this large peak and we see this low velocity extending beyond it. After the first layer, we see a small deviation in that, but as subsequent layers are added on, we see the system becoming more and more uniform. So as we go through putting in these layers of plaque, we're removing these areas where we had low velocity and vorticity, which is of course what's encouraging in some ways the stenosis to develop. Looking at the images here we're looking at time averaged properties. So the one on the left is the time averaged velocity. Very quickly to explain what all the lines on this show, the white lines, the vertical lines represent the end of the different layers. So when these different layers have been added. And so we can see during this first region, we've got a lot of change on this other white line. This white line here at an angle represents the extreme of the region where the stenosis is forming. And we can see it develops through the first layer, very little through the second layer, which is forming on the other artery wall, and then it starts to develop again. The black line is a contour plot through the low velocity region. It's been smoothed to give us an indication of where that region is. The rest of the results haven't been smoothed, but the black contour line has. And what we see is that as the stenosis develops, it develops more moving upstream, downstream rather, and less than an upstream fashion. Looking at the time averaged wall shear stress, we see a very similar picture, which sort of validates what I said at the start, that we can use the time averaged wall shear stress in place of the local velocity. Here we see the OSI, the oscillatory shear index, and the relative residual time, an indication of how long particles would remain in that region. In terms of the black contour, we see these values are very high in the regions where the velocity and the wall shear stress was very low, as we'd expect. We also see a region up here around about 47, 48 millimeters, which is quite high. That represents the region where I showed the oscillatory vortices earlier on. So that was present for some period of time, but then as the stenosis develops in the wall, we see that that region is no longer present. Also, we can look at the tangential component of that velocity U1 and RFI, which is a reverse flow index, which is basically the percentage of the period whereby the flow, the tangential flow, is negative. And we can see that these are rather different to the black contour. In particular, this region where we're getting low and negative velocities is concentrated around the region where the stenosis is developing and pushing along the artery wall, and doesn't show so much similarity to the black contour, which is the velocity 1 centimeter away, 1 lattice unit away. And we see the same sort of feature here for the reverse flow index. So in conclusion, we've been able to use this model to model stenosis growth, to model certainly the early stages of stenosis growth and looking at the development. We've seen that the stenosis has really grown to fill in the regions where we got low velocity and we got the vortex motion when we considered the original healthy artery. It progresses mainly downstream, particularly in the external carotid artery. And we see regions of low time average velocity and time average wall shear stress, and we see them developing around the downstream tip of that evolving stenosis. The facility shear index and the RRT, they showed similar behavior, but in the opposite sense. They were quite large where the other quantities were low. But we also saw a further region where the OSI and RRT were high, and we could associate that with the vortex motion that we observed in the healthy artery. I haven't said anything about the inner walls of either the ECA or the ICA. No stenosis developments were seen there, but we did see some changes. We haven't presented them here, but we did see some changes in the wall hemodynamics due to the stenosis development on the other walls. And I think we've got a fairly useful model here for understanding both the stenosis development, but also how that development affects the hemodynamics of the blood as it's flowing through the artery. So thank you for your attention. Are there any questions?
Okay, let's thank James for the presentation. If there are any questions, yeah, I see that Tim has one question, please.
Hello, James. So thank you very much for the presentation. It's always good to see that lattice Boltzmann is applied to biologically and medically relevant problems. My question is about the model you have for the growth. Have you considered different models, for example, models that are coupled to solute transport? Because what we have in reality, of course, there are certain chemicals being transported in blood, and some of them may actually affect the growth of the stenosis. But if you have a purely mechanical model, then you may miss the effect of the chemical. Have you considered this?
No, we haven't, but it's a very interesting point. We did focus this simply on the hemodynamics, so seeing how they affected the wall motion. But you're completely correct. I mentioned at the start all the other factors, things like obesity, but often that then affects the chemical elements in the blood and can affect the viscosity and things like that. And I think that's an area that would be very interesting to develop. I mean, in some ways, looking at the model, the region where the stenosis developed, it took out these regions of low velocity and low wall shear stress. Now, that's quite important because if we're looking at rupture, where you will get rupture is where you have high wall shear stresses. So that in itself is quite interesting. But it does suggest that the model may not predict further development because we're removing these areas of low wall shear stress and low velocity. So probably to look at further development of the stenosis, it would be important to bring in these other sort of biological and chemical factors.
Thank you.
Are there other questions? Okay, if not, thanks again the presenter for the presentation. The next and last presentation for this morning session will be held by Bastien Chopard about the anomalous platelet transport and flat-tailed distributions. Okay, please. Bastien, you can start whenever you want.
Yeah, so I'm trying to share my screen, and for some reason it doesn't seem to work. Okay. Sorry for that.
No worries.
No, it's not. Well, it seems that there's no way to share my screen here. So any hint on how I should? I got a message that Chromes want to share the content of your screen.
Perfect.
Where to share, and then I don't know how to go further.
Do you have a Mac or?
It's a Linux machine.
It's Linux. Okay, because probably it's a matter of permissions.
Okay. That's annoying that I couldn't do any test before. So
Okay, now it seems. Yeah.
but you see my screen?
Yeah.
Okay. You see the full screen?
Right now, yeah. We see.
Okay, very good. Okay.
Perfect.
So I'm going to talk about platelet transport and anomalous platelet transport. So for those who are not so familiar with blood, here you just have a snapshot of red blood cells and this yellow particle or platelet, which plays, of course, an important role in our physiology. And we're trying to understand how they move within this suspension of red blood cells and plasma. And as the title says, that I want to say that they don't move the way most people think they move, in the sense that they are not described by the diffusion equation. And I think it's a bit of a disruptive result that I'm going to discuss with you. And it will be based on the one hand, in vitro experiment, which started all our questioning because it was not matching the knowledge, and then a fully detailed simulation, as you can see, with Lattice Boltzmann. So this work is a joint work, and I want to especially mention the biologist of the team who is doing the experiment and is also involved in a medical environment. So we think there's also a clinical relevance to what we do. So it started basically 4 years ago with this simple experiment, which is referred to as IMPACT-R experiment. So it's a little container, like a cylinder, in which you put whole blood, and then you start rotating the top, and then you get a flow of platelet due to the movement of red blood cells. So it's called shear-induced diffusion due to red blood cells. And as a result, the platelet, they go down and they form little aggregate like this. And so each point you see is a platelet which stick on the bottom part. And the idea is that we can detect if platelets are dysfunctioning or not. So it's a clinically relevant test that you do. So basically what the experimental data gives you is the number of aggregates you saw on this picture at different time during the evolution. So we go up to 5 minutes of time. And you also get the number of aggregates, the number of black dots, and the average size of these aggregates at this time. But what's also very interesting is that we can measure the number of platelets still in the bulk at the same time. And the question we would like to ask from this pattern that we detect, can we get the adhesion and aggregation rate of platelet? Because if they are starting to dysfunction, that's this value that are likely to be affected by some disease. So the idea is from the picture, can we get this value? So that's the sketch of the experiment. Basically, you have here this deposition window, which is 1 millimeter by 1 millimeter, and you have a layer of blood which is about 1 millimeter too, and you impose a shear rate, okay? And in the blood, basically, we're interested in red blood cells. We're interested in activated platelet, non-activated platelet, and we found out that we also need to take care of albumin, which plays a very important role. So due to this shear rate, the red blood cells start moving and they push the platelet down to this deposition layer and they start fixing. So basically, the model that we propose to understand this pattern is to take care of the albumin, which is actually competing for deposition. And so it starts to fill in this little place where the platelet can deposit. But if there's not too much albumin, an activated platelet can deposit and fixed. And next to an activated platelet, a non-activated platelet can stick. So this is what we call adhesion, and this is what we call aggregation. And on top of this, you can also build some thickness so the platelet can pile up on top of each other. Okay, so that's the model we propose. And we use that model, and we, of course, had to calibrate some of this adhesion rate so that we can explain, that's the experiment, and that's the simulation. And you see a very good agreement if you put the proper adhesion and aggregation value. So basically, it's a way to measure this value. And if a patient has some disease, we could see some difference between this normal value. You see also there's a very good agreement between the volume of the aggregate and the distribution of sizes, okay, that we didn't use for the calibration. So that's something we get after we have calibrated this value. We see that in addition, we reproduce very well this finer aspect. So it looks like the model is really capturing well the behavior. The only thing which is a bit important and surprises us is that the diffusion coefficient that we use for the flux of platelet is this match. And I will, of course, come back to this because that's the key point for my story. So if you look at what's supposed to be this diffusion coefficient, so what's the mechanism that brings this platelet to this deposition? Well, it's known as the shear-induced diffusion, as I said, and it's described in the literature by this Sidney-Colton formula, which I give you here. So basically, it depends on the hematocrit, how many red blood cells you have. It also depends on the shear rate, which is there. But if you just apply this formula for our situation, you get 10 minus 11, okay? Which is different from the value we get to match the experiment. And actually, we can do even a simple check, which is just measuring how many platelets in the experiment have disappeared from the bulk during the first 20 minutes, okay? And basically, if you use the Sidney-Colton value, which is this one, you should have only 150 platelet per milliliter that has disappeared due to deposition. But if you do the experiment, you should find about 3,000. So there's a total mismatch of this thing. So you see that to explain what we observe, the number of platelets that disappear from the bulk, you need a diffusion coefficient, which is almost 3 orders of magnitude larger than the theory. So there should be something really wrong somewhere. And we started thinking about that for quite a long time. And we end up with an hypothesis that actually platelets do not diffuse. They don't have a Brownian-like motion, which is a Gaussian type of random walk, but instead they obey this so-called Levy flight, which means that their velocity distribution goes like a power law, okay, which is this one. This has consequences because this is a fat tail distribution. It means that you have big velocities, so large amplitude events that are not so rare, okay, that explain maybe that you have a much faster displacement of the platelet. And you also have the fact that with this type of relation, the variance of the velocity is infinite if alpha is small enough. So that's our hypothesis, and to check it, we went to a fully resolved simulation of red blood cells. So this is actually a software that we wrote entirely from scratch. So there's a finite element part for the red blood cell deformation. So it's a fully validated model for red blood cells that you can see here in this reference where it has been validated. It has been coupled to the Palabos lattice Boltzmann for the fluid part, and we have immersed boundary condition to do the interaction. So this is typically what we get as a simulation, and we're interested to see how the platelet, what's the random motion of platelet in this given situation, okay? But incidentally, I mean, we're also, of course, interested to study diseased situation. So this is a diabetes case where the red blood cells are different, but the platelet may also have some dysfunctioning, and we should disentangle the part which is due to the problem of the motion due to the red blood cells that are different shape, and the fact that the platelet may aggregate differently. Anyway, so back to the question is, can we determine the random walk that this platelet do in our simulation? And the first step is to determine the mean free time, so the time between collision. And this is done by following a trajectory of platelet and try to find a discretization which makes, you know, no difference between the fully resolved 5 time scale motion with this one. So the goal is to find at what time basically you experience a collision. And our conclusion is that it's about 0.1 millisecond. That's the tip which we should look at our platelet. Now, another thing that is important is that for low velocity, actually we have whatever we want for distribution. We're not so much interested in that part, okay? What we're interested is to understand what's the tail of the distribution. Is it a fat tail, or is it a Gaussian or something which is limited? And you can see here that we play with a lot of distribution, and I'm not going to go into detail, but it's all distribution which are fat-tailed and mean that they have big variance. So what we did, actually, which is important, and I think it was never done before in the literature, is to check the transport of platelet for bigger and bigger systems. So this is 50 micron, this is 100 micron, then we go to 250 micron and 500 micron, okay? And we compute what's called the mean square displacement. Basically is how far do the platelets move away from their initial position. And what you observe, which is very interesting, it's this black square. It increases as the system size increases. You see that the value of the mean square displacement increases, which is totally against a Gaussian type of theory for random walk. You also see that the fluctuation increases a lot. So basically, if you explain you write down what is the mean square displacement, you see that it's related to the variance of the velocity. But if the variance of the velocity is infinite for infinitely big system, you understand very well that you have to diverge. So that's the first indication that there's something important here, which is not Gaussian and tends to show that we have actually a fat tail distribution, so a non-defined variant. Here you also have something which is, another way to show it's not Gaussian is to compute the kurtosis. For a Gaussian random walk, it should be 0, and you see that you go to very high value and also very high fluctuation. So that's something, the force moment, which is not defined. Okay, so, I mean, there's something interesting here to say also. First, you should understand the size of the impact R experiment. It's still way too big to be simulated exactly with this fully resolved simulation. So the impact R is typically 1 cubic millimeter of blood that we want to run for 20 seconds, okay? And what we can do is basically 1,000 times less on 1 second, okay, in the space. And still we need the fastest supercomputer to do that. So it means that it's very delicate at this small size to detect what we want to detect. And actually what we discovered is that when you look at smaller size, like what is typically accessible currently to simulation, well, since you misunderstand this power law behavior with a Gaussian, basically you can be compatible with this value. Okay, that's a bit of a surprise. So it means that our results are not against what people found so far. It's just that because they look at too small systems, they couldn't see that actually it's more than that. And I will show you very quickly a visual explanation. So to see the effect, you need clinically relevant sizes to see this effect. I must say also that if you look at the literature, some people, they mention, oh, sometimes my platelets are doing something weird in my simulation, but it was never really, considered as a serious thing. But here we clearly go to this. So basically what we find is that with a lot of runs and a lot of fit and a lot of statistical work, we see that the distribution of velocity of platelet goes like this power law, a Levy flight with exponent typically 1.5 with some errors. And here you have a pictorial way of this. That would be a Gaussian random walk, and that would be the Levy flight with the same average jump. Okay, so they are comparable in the sense that the average jump is the same size. But you see that locally, you could misinterpret this as the same as that. You need some of these rare events to start seeing that it's very different. Okay, so now back to the impact R experiment. Can we understand why we have so many platelets that left the bulk during this 20 seconds? Well, we just need now to replace the movement of our platelet with this Levy flight, and we just get the right value with what we observe experimentally. So it means that we have an evidence that we have a Levy flight from this fully resolved simulation, but this Levy flight is totally compatible with the number of platelets that moved away from the bulk within this 20 seconds. Again, something we cannot reach with a fully resolved simulation. So as a conclusion, I think we are bringing here a very disruptive view of how platelets move in the blood, in the sense that this diffusion equation that you would like to use is not valid anymore. And if you still want a macroscopic description of the platelet, you need to go to this fractional derivative, which is a non-local system. It's a difficult mathematical object. Or you go to a purely Lagrangian description, which fits well with lattice Boltzmann, by the way. And I must say that this discovery is, of course, important for academic point of view, but it also a big impact on the way you analyze platelets for medical purposes. If you don't know how they move, you are likely to interpret them very wrongly. So with this, I'd like to thank you for attention and thanks the grant we got on PitStain for the computation and this funding from the Center of Excellence in Biomedical Science from the H2020 program.
Perfect. Thank you. I see on the chat that we have already a couple of questions. So please, the first one by Shalal El-Helul. So if you want to ask a question, yeah, please.
Sorry, I was in my microphone muted. So
okay.
Maybe it's a naive question, but when you look at the MSD, I can see that before I would go for Levy flights or something that is anomalous diffusion, I would think that I just have a ballistic component, because you look at the autocorrelation of the velocity and it seems that it grows. So if it was Levy flights, I would say that the expectation, I would look at the expectation would be 0 still. But when I look at your MSD graph, it looks like you have diffusion plus some advection, or you call it ballistic. So how do you know that it's Levy flight and not just a ballistic component?
If it would be a ballistic component, it wouldn't change with the size of the system, right? I think the key thing is that it's something which grows with the system size. It's not like if you have normal movement, it should have a ballistic motion with a given velocity, and then we should detect that whatever the size of the system is. The fact that you increase the system size is a sign that the variance is undefined and that it's a non-local behavior. So you have event of big intensity that appears.
So the Levy flights that you see are for both directions, against the shield flow as well?
We try only perpendicular to the shear flow. I think we probably get the same behavior in the direction of the flow. But since the impact experiment is perpendicular to the flow, of course, we are interested to that direction.
Yes, so if that direction only, then I would guess that you have an advection term rather than a random Levy flight.
No, you don't have an advection term in the sense that it's perpendicular to the flow.
So, but only on one direction.
Yeah, vertical direction.
So your average movement, not the mean displacement, but the average movement is not zero, perpendicular to the shear flow.
Actually, it is zero in some sense that you have both the same amount going up and down.
Ah, okay.
So it's perfectly symmetrical. There's no breaking, there's no symmetry breaking vertically. It's not like a tube where in a tube you of course have a difference between the center and the periphery. In this experiment, you can see also the distribution of red blood cells is perfectly constant across the vertical size.
Okay, okay. Thanks.
You're welcome.
Okay, let's do the second question.
Yeah, thank you. Bastian, great presentation. I have a related question. I think it's probably the continuation of the first question. I'm more interested in the physical mechanism behind flights or jumps or whatever. And if you think about the physical reason for the platelet diffusion, or let's say platelet motion, it's of course the motion of the red blood cells, right? Mm-hmm. And the red blood cells are larger than the platelets. And you also know that red blood cells can rearrange in space. Mm-hmm. I wonder if these events, the fat tail events that you observe, are they related to maybe a red blood cell pushing a platelet for a long distance? Can you explain what is actually happening in the moment you observe this kind of jump?
I think that's a very interesting question. The answer is we don't know yet. We cannot pinpoint the exact cause of this. But then if you go back to some, I don't have the author in mind, but there's an author who actually mentioned that there's like pockets between red blood cells. And he claimed that this pocket can close suddenly and push this platelet. Of course, when you read the paper, there's nothing about fat tail, there's nothing about rear event or whatever. But for me, it could be exactly what you're saying. So there is a configuration of red blood cells which is such that it gives a strong velocity to the platelet. But of course, we need to find the configuration of red blood cell that causes this. In principle, we could do that because we have the simulation, but it's a difficult analysis, I must say.
Yeah, I can imagine. Thank you.
Yeah, we still have a few time for the follow-up proposed by Ron Wertmann, please.
Yeah, hello. Thank you for the nice talk. Yeah, the follow-up is that if you actually think of hematocrit and if you reduce hematocrit, maybe you see the effect of what Tim was saying, the physical mechanism. Have you tried to do that, and do you see any difference? Do you see a shift from Levy flight to Gaussian behavior?
No, I think it's a nice suggestion. So far, I mean, it was a lot of work, I must say. It took us globally, I would say, a few years to come up to this conclusion because we had to build tools, the experiment. And of course, the next step is exactly what you're saying, is to see how this exponent alpha depends on the hematocrit. And if we have like a kind of a transition between Gaussian and Levy flight, that would be very interesting to see if there's a critical hematocrit. And of course, we also have to do this work for changing the shear rate, because it also depends on the shear rate. So there's still a lot of things to be explored. It's not so easy to do because this simulation, fully resolved simulation, are extremely costly. And experimentally, it's very hard to detect the motion of red blood cells, of platelets, because they are completely hidden by red blood cells. But I mean, your point is, it's a good suggestion to try out.
Yeah, I understand it's very difficult also to go to resolutions that are large enough.
Mm-hmm.
Yeah, thanks. I think this was very interesting to know. The behavior is not what you expect.
Yeah, thank you.
Well, if there are other questions, I think we may close the session. Thanks again to the speakers. We will move to Sala La Palma in a while. Sorry, Sala Leone in a while for the plenary. And thanks again to all of you for your contribution.
Thank you.